Alright, so what we want to do today, guys, is we want to start a new topic, okay? And in case you are not aware, this topic will go for about 3 to 4 weeks, approximately. It's under the heading of 3.3, and 3.3 is under the section of hydrocarbons. We're going to start off with hydrocarbons, but we'll eventually look at not just hydrocarbons, we're going to look at things called alcohols, carboxylic acids. We're going to do amides, amines, ketones, esters, all different types of organic molecules that you're all going to need to eventually take on board for stage 2, for year 12. Whoever's going on with year 12. Alright? Now, so this is a new section, as I've just said, and it's based on organic chemistry. Organic suggests living organisms usually, okay? This sort of stuff. So this is organic, like we're organic. So we're made up of a carbon-based structure. If you watch Transformers, what's the idea behind Transformers? What's that fictitious sort of group of things made up of? What's the base for a transformer? Silicon is the base, okay? So we just happen to be made up of carbon, luckily, alright? Because we probably wouldn't be alive if we weren't. So carbon is pretty cool. So anything to do with organic chemistry is carbon chemistry. So important that if you walk into at university or Flinders University, you'll see buildings dedicated to organic chemistry. It'll say the organic chemistry department. And then across the road, you'll see the inorganic chemistry department. Okay? And then down the road, you'll see the biochemistry department, all in separate buildings. Okay? Because they are in themselves branches of chemistry that get very detailed if you pursue any one of those branches. They won't call it that. So you'll see that in uni. If you get there. If you walk through this organic chemistry lab, you'll also notice a whole lot of horrible odours. Because typically people there, alright, in the labs are synthesising chemicals, sometimes chemicals used in, for example, drugs, alright? For positive use, that is, alright? So, many years ago I was involved in synthesising a drug that was helping students, but patients that were suffering from having fits. And so the lecturer said, here's the structure that we want to make, work out how to make that molecule. And so we had to work through it on paper first, and we had to go to the lab, and we had to try and make this particular drug, knowing that it had been, or had some positive effects on the person that was taking it through a drug trial program. So we were asked to produce this certain drug with certain groups in it, certain structures. Alright? Because it's an organic chemical, it interacted with the body. So the most drugs that we actually do take, okay, whether it's alcohol or aspirin or Panadol or paracetamol, they're all organic molecules. They're referring to steroids, bodybuilding, whatever. Hopefully not. But protein, for example, is an organic molecule. And you know that if you want to actually build muscle, you really have to increase your protein intake. So it's all organic molecules. 75% of molecules are based on an organic structure. Okay? It doesn't necessarily mean that when you go to uni that the organic chemistry department is 3 times as big as the inorganic chemistry department. They're still the same size, physically. Okay? We're going to start with simple organic molecules. Simple means they've only got hydrogen and carbon in them. And if you are not aware, a lot of the stuff that we use in terms of fuels, things like octane, petrol, is a fuel, and it's based on a hydrocarbon structure. If you've got a gas stove at home, that runs on butane propane. If you've got a barbecue, alright, with a gas cylinder, that runs on butane propane as well. So these are all fuels. So lots of hydrocarbons, not lots, all hydrocarbons ultimately are fuels. They combust, which we'll talk about a little bit later. Homologous series. Now, you should have done this in year 10. Is that familiar? No. Alright, okay. So, assuming you didn't do it in Year 10, no big deal. So homologous series is a group of organic molecules that have got some characteristic and they are put together in a family. We call homologous series like a family. But they are generated by a formula. The formula for alkane family, or the alkane homologous series, happens to be CnH2n plus 1, where n is equal to the number of carbon atoms. And so for this family called alkanes, the first member is called methane. The second member is called ethane. So this will be Cn, n is 2, H2n, that's 2 times 2 is 4 plus 2. That's how I end up with C2H6 for the structure. Or, some people will go the other way and just draw the structure, knowing that carbon's got a valency of 4, and they work out from the structural formula C2H6 for ethane. Everyone cool with that? Alright, so anything with an ane in its name, an ane typically is characterised by single bonds only between the carbons. That's really important. We'll come to that again in a few lessons' time. So ane, ethane, and then if we did all the homologous series, we'd only go up to 10. Okay? You can actually go up to 100 carbons, but we don't have to know those names. Alright, we stop at 10. So it's propane, butane, pentane, hexane, hept, oct, non, decane. You can look up others if you want to, and I think I've got it sitting in the sector lessons. So that's the number of carbons. So if I said work out the structure for heptane, it would be C7H14, 2N plus 2, 16. Should be C7H16 with the structure for heptane. And you could draw that. This is the molecular formula. You could draw the structural formula easy. Everyone happy with that? Alright, so that's just the alkane homologous series. We're not going to go into too much detail about all these homologous series, but you need to be able to actually to draw them, generate the formula each time if I ask you. Got to do that for the exam as well. So this one here is the alkene functional group. Alkene is double bond, only one double bond. We can also have things called dienes. We'll do that when we look at naming organic molecules. Again, next lesson. So we've got things like this one here. I didn't give you the name, but what would that be called? What would that be called if it's got 2 carbons? 2 carbons. Almost. Ethene. Ethene. This will be propene. Okay? So the ene tells us what the functional group is, or the homologous series. Ene is double, and the prop tells us how many carbons. So you've got to nail that, because we have to be able to actually name up to 10 carbon atoms in a single chain. Have to go up to dec. It's easy. If you can count to 10, you only need 10 fingers, okay? We don't go any more than 10, because we go more than 10 fingers, okay? We don't count toes, because just fingers is enough. Alright, so we've got things like ethene, propane, then it will be butane. Why is there no such thing as methane? Why does this not start at methane? Anyone work that one out? Excellent. Well done, Josh. So I cannot have like carbon and, wait a minute, I've got to have a double bond in it. But I can't have a double bond with hydrogen, because hydrogen's only got a valence. So the first member doesn't exist for the enes, and nor does it exist for the ions. And the ions are the triple bonds, not very common. So, same thing, alright, the first member here would be called ethine. Yeah, you got the idea. So, ethine, propine, the name sounds weird, but that's how we actually use the systematic nomenclature format that we'll talk about again in the following lessons. So, We've got alkanes, alkenes, alkynes. You should be able to draw and name all 10 members of the homologous series. Draw and name. Okay? If I gave you a structure, if I gave you, say, C3H6, you should be able to work out, is it an alkane, is it an alkene, or is it an alkyne? Okay? So you should be able to go backwards from the structural formula or a molecular formula, work out what homologous series it's from, or generate the structure. Alright, the next thing is just a very, very quick, the other thing is, these compounds, anything with a double or a triple bond in it, they are called unsaturated hydrocarbons. Unsaturated, meaning they haven't maxed out in the hydrogen. These ones are called saturated hydrocarbons. And again, have you ever heard of the word saturated and unsaturated in the food industry? Yeah. So where have you heard of those words mentioned?
Unsaturated fats.
Unsaturated fats. Excellent one. All right. So for those of you that are, say, carrying a bit of weight, which is none of you, but I am. Okay. So I have to be careful what I eat. So I'll try and stay away from saturated fats. Okay, because they're hard to digest and they end up being cholesterol in me. So I try to actually look at unsaturated fats. So I go for more plant-based, organic molecules, more plant-based oils, and I don't have a lot of meat, which are saturated fats, all right? Single bonds, hard to break down in your body, all right? So that comes up a bit later as well. All right, structures. Now, we spoke about this, I think, when we did the section on structural formula and molecules right in term 1. We might have talked about it then. So, here's an example of butane. All right, butane is an alkane, and we have to be able to draw structural formula, condensed structural formula, or skeletal formula, and bounce between all three. Okay? The structural formula has to show the three-dimensional arrangement of the atoms. That means all the carbons and all the hydrogens. Where are they? You can't just draw 4 carbons and not put the hydrogens on it. You've got to show the hydrogens. While I'm talking about structural formula, some people will draw structures like that and they'll put the hydrogen out here. But they're not really careful about how they draw the structure. That'll be marked wrong in an exam or a test. It just means you're not careful enough with your structure. So you've got to really make sure that when you're doing your structures, that they do line up properly. If that's the carbon that the hydrogen's bonded to, you've got to make sure that it lines up exactly on that hydrogen. Everyone cool with that? All right, now, so structure we've done before, that's a given. Can you remember why we do organic molecules in a straight chain? Why do we just do them in a straight chain? Because actually they're not, If I grab this compound here, which is propanol, this is an organic molecule, it's an alcohol, is that a straight chain? No. It's obviously going to be 1,10, what's tetrahedral bond angle? 109.5 degrees is the angle that it will be, But for simplicity, when we're drawing organic molecules, we actually draw them as if they're 90 degrees, but we have to remember they're not actually 90 degrees. This is actually how it should look. So really, alright, if I were to do the molecule for butane, and I'll just create butane from my little kit, from here, butane actually would look like this. In real life, there it is, that's a butane molecule, CH3, CH2, CH2, CH3. So there it is, How can I do a condensed structural formula? Well, I put all the hydrogens together. It's a bit tidier, Now, you can also do another one here. You could actually do it like this. You can do CH3, CH2, CH2, CH3. Provided the sequence is correct, it doesn't matter whether you put dashes between the carbons, whether you group the CH2s together, alright? Condensed structural formula is pretty flexible in terms of how you use it, The only thing you couldn't do here, you couldn't say CH3 bracket 2, CH2 bracket 2. You've got to actually show the CH2s where they are in the chain, sorry, the CH3s where they are in the chain separately. Okay? And this one here, skeletal structure. So what have we done? We've got rid of all the hydrogens. So it's only the black carbons is that we're seeing. And whenever I said we're working with skeletal structures, what was the key there? So if I give you a skeletal structure of anything, what would you be doing with this structure before you did anything? Add the... You should be putting in the carbons so you can actually see, and then you should be putting in the hydrogens. 1, 2, 3. Must be 1, 2 there. 1, 2. 1, 2, 3. If you don't put in the carbons and the hydrogens, you can miss out carbons really easy in skeletal structures. And we'll actually use those. So if I gave you a structure like this, looks pretty weird, but what's that the structure for? Skeletal structure? That would be the structure for? It's on the board already. Which one? Methane. Try again. Bute. There's not 4 carbons there. How many carbons are here? 2. 1, 2. Okay. How many hydrogens? Well, you fill them in. 1, 2, 3, 4, 5, 6. C2H6. That will be the structure. Did you say ethane, Josh? Sorry? Yeah. Ethane. No, I said methane. Did you say methane? Yeah. Okay. It's actually ethane. Alright, that's all we're going to do today on that. Just get that copy down and we can move forward.